This is the experiment for the measurement of Planck's constant. Aim of this experiment is to determine the Planck's constant and to verify the inverse square law of radiation. So in this experiment, from our manual, we can see the apparatus required is the vacuum phototube, halogen tungsten lamp, color filters, regulated voltage power supply. So these are the specification, range detail and all. And experimental setup, if we check our lab manual, we can see this is the apparatus and the basic principle involved in this one, the schematic. We can see the light, this is the light source. It is falling into the photocell, as a result of which when light will be falling in the photocell, the current will be produced, and that current will be getting in the outer circuit, and when we will be applying some negative voltage to stop that photocell current, then we can measure the stopping potential. So our aim is to find the stopping potential first, and from the stopping potential we can plot the different. Actually, if we go to our table, so there we can see for the different colors, so like the red, yellow 1, yellow 2, green, blue, for all these different colors we need to find the retarding potential. What is retarding potential? Just now I told you that it is the stopping potential. When the light will be falling in the photocell, the electrons will be ejected out of this cell, and you will be getting an external current in the circuit. So to stop that photocurrent, we need to apply negative potential across this photocell, which is also known as the retarding potential. When it will be stopped, means the current will be stopped, that is the current value will be equal to 0, then that value of the voltage will give you the retarding potential. So we'll be applying for different wavelengths. You see these are the different wavelengths for different colors. You know, in the VibGeo, all the colors have different wavelengths. So according to the color, we'll be getting the wavelength. Once we know the wavelength, we can velocity of light we know. So frequency we can calculate. We'll be putting the frequency over here, and the retarding potential will be getting from the experiment. Once we get this, we'll be plotting the graph. We'll be plotting the graph, and we'll be getting, if it is correct, we'll be getting a straight line. We'll be getting a straight line. Now to verify the inverse square law, what we'll be doing, we'll consider one particular filter, that means the red color one, and then we'll be applying anode voltage, which is fixed at 0.25 volt. We'll fix it at this particular voltage, and then we'll vary the distance of the light source. If we vary the distance from 18 to at 2 centimeter distance variations, 18, 20, 22, then 24, 26, 28, 30. Then we'll take the inverse of this distance, which is in centimeters. So inverse of the distance will be in per centimeter square, and the corresponding current will be getting from the apparatus. That will be noting down over here. Once we get these two values, then this taking these two values, 1 by r square along this x-axis and this current value along the y-axis, will be putting, and we will get this graph. So if this will come as a straight line, then only our experiment is verified. Now, so for the calculation part, we need to draw the graph for the variation of the stopping potential with respect to the frequency, which is given in the table, first table. Okay. So the Planck's constant can be calculated from the slope of the straight line employing equation 3. So it is there in your theory, the equation 3. Slope of the straight line we can find out once we get the straight line, then we can find out the slope. Once we get the slope, then Planck's constant, which is also known as H, the electronic charge into the slope will give you in joule second. Okay. The intercept of the straight line on negative y-axis, if you notice the intercept, it is not cutting the y-axis on the positive side, rather it will cross the x-axis and it will intercept the y-axis along the negative side of the y-axis. So that will give you the some value of the y-axis, and that value will be in volt. Thus, work function we can find out from there. So that intercept will give you the work function, which is in electron volt, you can find out. So that's how is your whole experiment is designed. So after that you need to find out the result where you will be writing the H value and phi value. In the discussion part, whatever is given, you will write 2-3 points for discussion and sources of error or precautions. So I'll show you the actual apparatus for this experiment, which is nothing but this one. So you can see the apparatus. This is our apparatus, and this one is the light source. This one is the photocell, and here the vacuum tube is there, the cathode is there, or the where the light will be falling, and the electrons, photoelectrons will be coming out, and inside this the circuit is there. Here the circuit is shown. Now this will be used as ammeter as well as voltmeter. There is a two mode over here. If you put this one on this side, this knob, then it will measure the current in microampere. And if you put this one on this side, this meter will measure the voltage. Okay. So similarly, on this side, the voltage direction is also indicated. Here, this one is the negative side. When you need to put the voltage, the retarding voltage, you need to put this knob towards this side. Look at this. This is the negative sign. So you are applying the retarding potential. So you can see this is the photocell where the light will be falling, and as a result of which across this photocell you can measure the voltage. This will be reflected over here, and this current will be passing through this circuit, and the current can be measured over here, microampere. And if you apply some voltage, that is the negative voltage, to stop this current, then you will be applying through this part. Through this part, this is the potential, this is the voltage regulation. So if you apply the voltage from here, then that will obviously at the negative side, then that will reduce the current. That will reduce the current. Ultimately, our aim is to stop that current, okay, due to the photoelectric emission, whatever current we are getting. So due to that photoelectric effect, whatever current we are getting, we need to stop that current, then only we will be getting the retarding potential. So let us start the experiment. Let me put this one at a particular distance. It's irrespective of anywhere you can fix it. Where some value is given in your lab manual. If you follow that, it's okay. If you do not follow, or if you maintain some other distance, then also there is no such problem. But it's better to follow the instruction given in your lab manual. So before starting, I want to show you the filters, because when I say the light will be falling into the photocell and it will be of different colors, then we need to put these filters. So when light will be passing through this one, white light will be generated from here. And when this light will be passing through this red filter, then the red color only can enter into this photocell. So similarly, if we use the different yellow colors, look at this is the yellow colors. There are two yellow colors. This another filter, then the blue color filter, then the green color filter. So we have this many 4-5 filters. We'll start this experiment with the red one. This is just to, this is the cap to put this one in, like while it is not in working mode. So now we'll be putting this red one into this cap position. Red one. I have put this light at a distance of 30 centimeters. My knob retarding potential is over here. And look at this multiplier. This multiplier means whatever you will be getting over here, this is the multiplier. So we need to put the multiplier at this point 001. Okay, particularly for this position we'll be putting, and then we'll find the current value. Let us see what happens. I am switching on the apparatus. Okay, light is coming from here. It will be passing through the red filter, and we're getting some, this is the current value we are getting. Okay, now what I can do, I can change the potential. My stopping potential I have given, in spite of that some value is here. Okay, I don't want this current. So to make this current 0, I need to increase the stopping potential. Look at this side, it will be increased. If you rotate this one in the anti-clockwise direction, so I have to make this value is 0. Okay. So look at this, it is decreasing as I am rotating this one in the anti-clockwise direction, right? So I need to make this as 0. 0, 15, 0.00. Done. So we are getting this current from the photocell, it is equal to 0. So what I need to find out, the retarding potential. How to measure that retarding potential? As I told you, this meter can be used as the ammeter as well as voltmeter. So if I change the direction of this knob, you will be getting the negative voltage, which is equal to 0.38 volt. Look at the unit, it is volt. So for this particular red color, we are getting this retarding potential is equal to 0.38 volt. Similarly, we want to find out for other colors, let us say yellow 1 and yellow 2. So this is yellow 1. So let me put this one. Now I need to make the current 0. Okay. Look at this. It is not 0 now. Previously for the red color it was 0. So for the same retarding potential, it is not equal to 0. So what I need to do, I need to make the voltage retarding potential I need to increase so that it will become 0. Okay, so you need to note down the color as well as the retarding potential. Our aim is to plot the graph, so I need to find out the retarding potential at which the current value will be equal to 0. Look at this, it's becoming less and less value when I rotate this one in the anti-clockwise direction, right? 0. So now what I will do for this particular yellow one, I am measuring the voltage which is equal to now minus 0.76 volt. Okay, once I get this one, I will be measuring another color, is the yellow 2. So let me use this yellow 2 color for this particular one, and let me check the value of the current. So now it is negative, these things means negative current, which is due to the retarding potential. So I have to reduce this one. So this for this particular yellow 2, we have to decrease the value of this potential, retarding potential, to make it 0. We don't want negative value which is more than the photoelectric current due to the retarding potential. Now it has given 0. So actually this is our yellow 1, and just previous to this that was yellow 2. Okay. So we can measure the retarding potential. This is equal to 0.62 and that was 0.76. Okay. After noting down this one, we need to go to our next color, and that color is as it is given in your manual, green color and blue color. Okay, look at this, green and blue. So we'll be putting this green color. Look at this. Now let us check the value, the current for that particular retarding potential. It is not equal to 0, rather we need to increase this negative voltage so that the value will be equal to 0. Okay. So look at this value of the current. Over here it is decreasing and decreasing. So yeah, 0. So once you get the value 0, you check the value of this voltage which is increasing, retarding potential. So 0.95. So at last we will be putting this blue color, and let us change this to this one and see the value of this one. It is having still some value. We have to increase the retarding potential by rotating this one. Our aim is to make this current 0, and we are getting this one 0. Okay, and then we will be finding the value of the voltage retarding potential. In this case it is 1.16. So after taking all these readings, what we will do, once again we will be putting this color, red color. Okay, red color, and look at you can even switch off this one, because it should not be on for a very long time, then sometimes it may be hot or this light may be disturbing. So sometimes you need to give rest of your apparatus also. So for the verification of this inverse square law, look at the process. Here what you need to do, this is the process, choose a particular color filter. So we are choosing the red color one, okay, in front of the photo tube. Set the voltage direction switch at positive side. So till now whatever we have done, it was at the negative side. Why? We want to find out the retarding potential. Now we don't want to find out the retarding potential. Our aim is to verify the inverse square law. Hence we'll be changing the direction of this knob, okay, for the voltage. Then positive side. Now keep the voltage at a fixed value. So value we have put as 2 point, or that already been instructed in this manual. So which is anode voltage for the inverse square law. Our anode voltage is given as 0.25. We have taken the red color filter, and for the red color filter it is, the wavelength is this, okay, fine. So everything is set. Now we'll switch on once again after changing the knob, the direction for the knob. Then let us switch it on, and as it has been given the instruction, our value will be at 0.25 volt. So let us reduce this voltage to 0.25 volt. This one should be, look at this direction of this knob, it is at voltage side, and this value will be at 0.25. Look at this value. I am reducing this one by rotating. This time I am rotating this one in the anti-clockwise. For reduction it is anti-clockwise. For increasing it is clockwise. Okay. So, and the symbol is also given from this. This shows that this side it is increasing, this side it is decreasing. So I'll be making this one as 0.25, right? Okay, 25. That is done. Now look at this table. We have started from 18 centimeter, 20, until 30 will go. Okay. So in the reverse order also you can do. There is no problem. So let us go to the last one, since it is there already at 30. So we'll go in that order. So 30, 28, 26, 24, 22, 20 and 18. Okay. At this particular value, our current is to be measured. Current is to be measured. So to measure the current value, we need to shift this one in this direction. Okay. And this time it is 1.42, or if it is increasing, then just take the average value of that. There is no problem with this. Okay. So if it is not stationary, you have to check the values or the range in which it is changing, and you take, if you take the highest value, you take highest for all the readings. If you take the lowest value, you take the lowest for all the readings, and if you take the mean value, you follow the mean value for all the readings. Okay. So at 30 centimeter, it is 1.4450, let us say. Okay, 50. The lowest value will be taking, and that is, it is showing 50. Then the next value at 28 I am changing the distance, and this time it is 1.692. That is the lowest value. Okay, 1.692. Okay, since I am taking the lowest value, I will be taking lowest value for all the distances. Next reading at 26 centimeter, and this time it is 1.87 or 1.86. Let us wait for the lowest value. 1.8. No, it's increasing. Yeah, 1.869. Okay, that is the lowest value at 26. Then at 24, look at this. Now it is showing 1. It means it is beyond its range. Okay, so we have to change it from here to here. So we can get the value. It is 2.09. Sorry, 3.09. No. Let us wait. Lowest value will be taking, and this value is equal to 2.12. 2.12. Okay. Now let us go to this from 24 centimeter to 22 centimeter, and here we are getting 2.99, 2.42. Something 2.4, yeah, 2.46, 2.46. That is the lowest value we are getting. Okay. So after noting down these readings, we will be moving to from this position to 20. Okay. Let us say 20. So at this position we are getting 2.91. Right. After noting down this 20 centimeter and this readings, we will go to 18. Okay. At this position it is 3. Let us wait for the lowest value, 3.32. 3.32. Okay. All the readings, the current value with respect to the distance I have measured. Now let us switch off the apparatus, and I'll show you how to plot the graph. So you can see the plotting, something along this is the inverse square. So yeah, so this is the frequency versus retarding potential. Okay, so look at this graph and note down the scale properly so that you can get the idea. You need to find the slope from here to get the value of this h, and you will be getting this interception at the negative y-axis to get the work function. Okay, and it will be a straight line like this, and the scale should be 10 smallest scale division is equal to whatever you consider. For this particular one, it is 0.25 volt, or it is along the frequency, so it is frequency will be in hertz. Okay, it is given, and its order should be written properly. For this particular one, the unit is the wrong, and so 10 small along y-axis in terms of 10 smallest scale division is equal to, here it is written, 2.5 into 10 to the power 14 hertz. No, the scale, it has been written in opposite way. The frequency along the x-axis, retarding potential along the y-axis. So even though here it is written, I have chosen the wrong. The student has done it in the opposite way. The x will be the y and y will be the x for the particular scaling. That you correct it, do not follow exactly what is written, but follow whatever I said. This will be, the y-axis will be in the volt and x-axis will be in frequency or hertz. Okay, if you follow this for the first table, you will be getting the h value as well as your work function value. And to verify the inverse square law, you need to use your second table, and by using the second table, you will be getting the inverse square law. It is a straight line. Okay, this is the 1 by r square. This is 1 by r square along the x-axis, and this side the current value. This is the current value in microampere. Okay, after changing the potential direction as I have shown in the apparatus, then all the points for different distances you need to put corresponding to the current value, and it will be a straight line like this. If you get a straight line, then this inverse square law is verified. You need to write the scale properly. Okay, and that's how in the result, whatever value you will be getting, that you will be writing in your result part. After that, you will write the sources of error and precautions, and that's how your this experiment will be over. Once you finish up your experiment, take out this red filter, and instead of this, you put this cap so that it will not be, it will be protected. Okay, and to its respective position at around 30 centimeter, put this light and switch off the apparatus. Do not keep the apparatus in on condition for long time, and switch off, put this knob at 0.001, because next whoever will be performing the experiment, they need to put it over here. So in whatever condition you got the apparatus, you need to put it or restore it in the same condition. Okay, thank you.